So, we move on and we look at the predecessor of a PLC. Actually, as we have said that PLC is just before the PLCs were invented or made out of microprocessors, such sequence control problems used to be typically tackled using control panels, which typically employed things like relays, contactors, various kinds of switches, lamps, various kinds of electromechanical timers and such things. So, they were actually physical devices which were hardwired. So, they were typically arranged for ease of maintenance and installation, etc. They were typically arranged modularly. So, the typical arrangement would be that there will be a positive voltage bus bar and there will be a negative voltage bus bar, and you will implement a particular logic, that is you will implement basically a network which is a series or parallel network, of various kinds of switches. So, under only certain specific conditions of these switches, there will be a connection from this point to this point. Otherwise, under other conditions, these two ends will not be connected. So, when they are not connected, the voltage will not appear here and therefore current will not flow. And so, whatever this output is, this is sometimes used to be called an output coil, because they were typically physical devices like solenoids or motor starter coils. So, they are typically coils, so they are sometimes called output coils. It's a legacy, they are still sometimes called output coils. So, then the current will actually flow through this. So, it is therefore, by this switch network you can actually control the situations under which this output is going to be excited. So, this is the way things were made, and when PLCs were made initially, see, you can always make a new device, but it is relatively more difficult to change the training and the mindset of the people who use them. So, just respecting the background of the practicing engineers, the PLC programs, see, PLCs are nothing but microprocessor based systems. So, if you see, essentially PLC programs are nothing but assembly language programs. However, just so that people can write them and people can interpret them better without making mistakes, so therefore, a graphical kind of programming language was evolved and it was used so that the engineers could think in terms of relays, and then using some tool, such pictures, such relay connection pictures could be transformed to an assembly language. So, that is why programmers have to be used to convert such graphical programming language which resemble relay ladder logic, physical relay ladder logic, and they actually get kind of compiled into an assembly language program or a machine language program, and they run on the PLC. So, the kind of PLC programs that we will see, they will also be organized like relay ladders, while there is no real relay here. So, we will draw these power rails which are virtual, because this is entirely an abstraction, and each one of these program statements will be called a rung. So, actually these relay ladder logic programs are nothing but a series of rungs having between two rails which are virtual. So, the left part of the rung is a network of the various ladder logic elements like various kinds of contacts, timers, etc., and followed by an output coil which shows under what condition that output is going to be excited. So, this is the way we are going to draw them. So, coming to the so now we have to understand, So, you see that how the PLC program will be executed. So, one after the other starting from the top, after the inputs are read, program execution is simply executing the logic of the rungs, evaluating the output values from the top one after the other. So, typical program flow is from the top. These are individual rungs. Now, you have several logics and they are all executed between one input read and output read. So, it may appear to you that in what order you are going to put these logics one after the other is actually immaterial, it makes no difference, but it does. For example, imagine that you are, sometimes what happens is that when there is a very complex logic, then you sometimes break up that logic into several parts. So, what happens is that initially you evaluate some small part of the logic, you compute some value, then you use that value and you put it in another expression and then evaluate something else. So, it may happen that finally we want to compute the final output. The final output can be computed based on some intermediate result D, which can be computed in terms of some intermediate result C, which can be computed in terms of B, which can be computed in terms of A, and finally the input, A can be computed in terms of the input. So, you have essentially broken up the logic into these 5 different steps. Now, if you write it like this as we have shown, then what will happen is that first, suppose the input is read, which is supposed to cause a change in the output. Now note that these are actually nothing but internal variables. These D, C, B, A, these 4 are just internal variables. They are just memory variables. So, when you will evaluate output, you will use the old value of D, which was computed using the old input. So, therefore, output will not change in this cycle. However, similarly C will not change because and D also will be updated because we will use the old value of C. Similarly, C will not be updated, similarly B will not be updated. However, A will be updated because now you have got a new value of input. In the next cycle, this changed value of A will cause a change in B, while C and D will still remain, C, D and output will still remain unchanged. So, in this way, just because we have organized these programs in this fashion, we will get a 5 scan cycle delays between an input read and an output change, which is completely unnecessary, because if we had organized it in a slightly different way, then what would have happened? Suppose we just invert the order, then in the first cycle input will change A, so A will get changed in the first cycle. Now, when we evaluate the second one, we contain the new value of A because we are taking it from the memory and the memory has been updated. So, and similarly when B is updated, C will be updated, when C is updated, D will be updated, and so in the first cycle itself output is going to be updated. So, this is something to be remembered, that the program flow should represent the actual flow of logic, that is what causes the other when one is developing relay ladder programs. So, now let's look at some of the elements which occur in a relay ladder program. So, the simple elements of a relay ladder. Today we will look at, there are various kinds of elements. Today we will look at 3 kinds of elements, namely we will look at as we have already seen that there is an output coil at the end, and we have also seen that it is like 2 rails, then some logic, and then finally an output coil. So, this is logic. Now, today we will study where the logics are just made of some input and output contacts. In fact, they can be made of many things. They can be actually these input and output contacts are, those who have studied digital electronics, they are like combinational circuits, while we could also put other elements in this, within this logic, to make this logic a sequential logic using timers and counters and things like that. So, that we will see in the next lesson. Today we are going to see circuits which are made simply of various kinds of switches. So, basically combinational logic. So, before we change this, we must mention that there are now these switches are of two types. Some of them are called input contacts. So, they correspond to, these contacts are physical, they are abstractions of real physical inputs, like some photo detector has detected a part. So, it has changed from 0, it has gone to 1. So, that one of the, so an input contact will correspond to the physical photo detector device. Similarly, there may be a limit switch, or there may be a pressure switch. So, these are, or there may be a push button which the user pushes physically, maybe the operator pushes. So, such contacts will be called input contact, which are externally exercised by the machine, that means external to the PLC, and which are real, that is, there are corresponding to these contacts, there are real physical devices. On the other hand, sometimes we will use some memory variables as contacts. For example, as we have said that we can use some value of the output coil. Suppose the output coil value of the ith rung we may use in the jth rung. So, how are we going to use that? So, to use the value corresponding to an output coil, we will create a contact. Such contacts are called auxiliary contacts. So, they have no physical existence, they are simply just memories, okay, and they are used actually for logic evaluation, and they are exercised when an output coil is energized. So, these auxiliary contacts correspond to output coils. And finally, an output coil is also corresponds to a physical output in the real external world. So, now, these are the three elements with which we first will construct our simplest PLC programs. We will use two types of contacts. The first kinds of contacts are called not no contacts, they are NO contacts. NO means normally open. Similarly, so this means that when these contacts are not energized, or they are in the, they are unexcited or de-energized states, then these contacts should be assumed to be open, because we always interpret PLC logic as if some switch is going to open. So, we are always looking for closed paths on the RLL programs. So, when that contact will, for example, when a push button is not pressed, if it is represented by an NO contact, then when it is not pressed, that contact in the RLL ladder logic is going to remain open. So, we must interpret it that way. Similarly, we might have what is known as an NC contact, where NC stands for normally closed. So, the same push button, if we represent it by an NC contact, then if the push button is not pressed, that is when it is not excited, that contact will remain closed. So, we must interpret it that way in the PLC logic when we try to see whether there is a continuous path from the positive rail to the output coil positive end. So, it is open when energized and it is closed when de-energized. Now, we will look at a very simple example. This is an example which is it's a simple version of an example which is used typically for, let us say, motor control. So imagine that we have a motor and we want to, there are two push buttons. One says go forward, so the motor will rotate in one way. It could be a movement of a motor, it could be a movement of a plunger in the forward direction. Similarly, there is another push button which says go in the reverse direction. So how is this achieved? This is typically achieved by, if current flows in, so maybe there is some solenoid somewhere. So if this is positive, this is made positive, this is negative, current will flow in this way and then the motion will take place in one direction. On the other hand, if this is made positive and this is made negative, then current will flow in this way and then probably the motion will take in the other direction. This is the way it is done. So therefore, sometime you have to connect the positive terminal to this point and sometimes you have to connect the positive terminal to this point. Now a potentially hazardous situation exists, that is, if by chance they are two different switches, if they are pressed together, then what is going to happen is that the positive terminal and the negative terminal will get shorted. This may cause an accident. So we want to have a logic, we do not feed the push buttons directly, rather than we take it through a PLC, so that we ensure that even if they are pressed together, no such problem will occur. So now we see what is going to happen. So you see that these two push buttons, corresponding to each push button we have two contacts. So corresponding to the first push button, which we called IN001, we have two corresponding to IN001, yeah, okay. Now you see, sorry, this IN001 is actually a master control switch. So nothing will happen, see the motor will not rotate either this way or that way unless this switch is pressed. So this is like an emergency stop, you know. This motor has three modes. So it has a mode move forward, it has a mode move reverse and it has a mode stop. So if this is actually a stop switch. So you see that, and these are the two output coils which you can say symbolizes the arrangement of switching the power supply to either the positive and the negative. So when this becomes 1, when OP001 becomes 1, then the motor gets supply in one way, and when OP002 becomes 1, the motor gets supply in the other way, and when both are 0, it does not get any supply, so it is standing. So we see, first thing we see that these are normally closed switches, and when IN001 is excited or the stop switch is pressed, then these will become open because they are normally closed. So therefore, obviously there is no question of this positive rail, they are getting a continuous path to the output coil. So both will be off, fine. So we have satisfied that condition, that is the stop switch is pressed, it is going to be 1. Next, suppose the stop switch is not pressed, so it is off. Now if we pressed, suppose this is a push button, this is, let us say, forward. So if this is pressed, now you see initially both are off, so therefore this is also on and this is also on. So when this is pressed, this will become on and there will be a continuous path to the output coil. So this is the forward coil and the motor will start moving forward. Now note that this is an auxiliary contact. So the moment this gets supply or becomes 1, this is going to be excited. So this will be closed. Now even if you remove this switch, it is a push button. So you have to press it and then you can release it. You can't keep holding it. So you press it once and immediately, even if you leave it, the motor will keep running. That is the arrangement that we have to make. So that is made by this parallel path. So, after this has become on, even if this becomes again this becomes open, there is still a parallel path, and that parallel path is this one. So, this forward coil continues to get supply and the motor continues to rotate. Now, in this position, while the forward coil is on, suppose somebody presses the backward coil or the reverse coil, what is going to happen? So, then this will become on, but interestingly nothing will happen, that this coil will actually not get supply because of this one, which is another auxiliary contact. So, whenever this is on, this becomes excited and this becomes open. So, this will be open, which means that even if this is already open because this is off. So, even if this becomes on, there is no, the continuous path stops here because this is open. So, therefore, this cannot be excited while this is on. If you have to excite it, you have to first press the stop switch, by which both will become off. This time you can press this one, then this will become on, and similarly when this is on you cannot press, you cannot make this one excited. So, this is a standard forward reverse interlock which ensures that simultaneously you cannot command the motor to move both ways. Before we end, let's look at another example. So, what are the elements? So, the elements of the example are the IN001, which is the stop push button, IN002, which is a forward run push button, IN003, which is a reverse run push button, and the output coils are forward starter and reverse starter, and the auxiliary there are auxiliary contacts NC and NO also corresponding to these. So, there are NC, there is one NC and there is one NO. Oh, I am sorry. Anyway, that we have studied. So, now let us look at the second example. This is our old die press, and we know its behavior. We have seen it in the earlier lesson. So, now we have to design a controller for it, a control logic for it, such that whenever a die is, that is whenever some switch is, master control switch is pressed, it keeps on going through a cycle. Okay. So, so we will see its simplest version. So, it's very similar to the forward reverse control, because here also there is a forward reverse motion. Only thing is that so you have a master control switch again. So, if the master control switch is if it is master control stop, it is kind of emergency switch. So, if it is flicked, then this machine does not work. So, neither up solenoid nor down solenoid will get supply, that is fine. Now, initially suppose the press is in the bottom position. So, the down lamp, that may be the parking position or the shutdown configuration. We are not discussing how it will come to the shutdown configuration. We are just saying that from the shutdown configuration, if it starts, I mean, how does it start? So, because the down lamp will be made, so this will become on. The moment, and so initially down lamp is the, so what will happen? So, it's down, and because the down solenoid is this, because the down solenoid is off. So, therefore, this actually is, we should have this as an NO contact. So, then this will become on, it will become oh right. So, correct, it is an NC contact. This down solenoid is off, so therefore, it is closed. So, when the down lamp is closed, immediately the up solenoid will get supply. So, when the up solenoid gets supply, again this will become, this is an auxiliary contact. So, it becomes on. Now, there is a path through this way. Note that as it moves, so immediately when the up solenoid is on, the press will start going up, and when it goes up, the down limit switch and the down lamp will glow, will open. So, even if this opens, but the up solenoid will be on and it will keep going up. Now, the point is that it must stop somewhere. So, when it will reach the uppermost position, at that time the up lamp will glow. When this will be glowing, this will become open. So, then the up solenoid will become 0. So, now the up solenoid becomes 0. So, therefore, this is closed and the up lamp has grown. So, this is now closed. So, immediately the down solenoid will now get supplied, and when the down solenoid gets supplied, this is closed and the down lamp is anyway not excited. So, therefore, it will start coming down and then the up lamp will open, but still there is a path in this way and the down solenoid will keep getting supply, and so the press will keep coming down under hydraulic pressure. So, you see that using another contact we have just ensured that there is alternating motion. So, these are the two examples of RLL that can be constructed with simple contacts. To review the lesson, we have seen three major topics. One is a PLC program execution. The second is we have seen the simple RLL programming elements of NC and NO contacts and input and auxiliary contacts as well as output coils. And finally, we have seen two simple RLL programs which have shown that how to create interlocks and how to create alternating motion. There are some points which you could test questions or points to ponder. For example, what is the difference between the execution of programs in PLCs and that you could write in a normal PC or a microprocessor, as we have seen that the difference is in the way input output is done. What is the basic difference between normally closed and normally open contacts, and input and auxiliary contacts, and it will be interesting to see that what could be possible defects. We have the die press controller that we have given is a very simple controller. What could be possible defects with it? And finally, it will be good if you can try to draw your own RLL program for the control of a pump to keep the water level in a tank below a mark. So, imagine that your house, in the house you have put some PLC control such that you never run out of water and it will sense the water level. So, a very important part before designing the RLL is to identify the inputs and the outputs of the controller, what sensor you are going to use, what are going to be the outputs of your PLC, etc., and then try to write the RLL program. So, that is all for today. Thank you very much. We will see the next lesson in the next class. Thank you very much.